Okay, this is section 4.2, polynomial functions. First, the definitions. A power function is a function that can be represented in the form f of x is equal to x to the p power, where the base is a variable and the exponent p is a number. Okay, and down below here we have some graphs of power functions. On the left here we have graphs of power functions where the power is an even number, and on the right we have the graphs of power functions where the power is an odd number. Something important to notice is that the higher the power, the faster the function grows or goes off to infinity. Okay? The lower the power, the less quickly the function grows, or grows in the negative direction. Either way. End behavior, also called the long-run behavior, describes the y values of the power function as x approaches positive or negative infinity. Okay, so the idea here is as your inputs to your function, your power function, get very large in magnitude, meaning we don't care about the sign, we just care about how big of a number, how far the number is away from zero, then the function behaves a little differently. We see here, when you have an even power function, the graphs go up for positive values of x and negative values of x. Okay, so that's this case here, right here. But notice that when you have an odd power function, it's different, right? So as x gets very, very large, the outputs of the function also get very, very large. Okay, so that's this case right here. Or as the x values get very, very large, but in the negative direction, the y values also get very large in the negative direction, and that's this case. Okay, so this will be very useful for us when graphing polynomials, is to know the end behavior. In fact, for graphing polynomials, we really need to know two main things about the polynomial. That is the long-run behavior and the short-run behavior. We'll get to short-run behavior in just a moment. Okay, a polynomial is a function of the form, you see here, I'm not going to read this out loud or even attempt to, but what is this? Basically, it is a sum of scaled power functions. Okay, so you see the a sub n minus 1, a sub 2, a sub 1, a sub 0. Those are called coefficients or scalars. Scalar, coefficient, they're just fancy numbers for numbers, right? And so a polynomial is a sum of scaled power functions. Okay. A term of a polynomial is any one part of the polynomial. So here's the first term in the polynomial, the second term, and so on and so forth. A term is just the scalar and the power times the power function. The degree of a polynomial is the highest power of the variable that occurs. So this polynomial is degree n. Finally, the leading term is the term with the highest degree, and the leading coefficient is the coefficient of the leading term. Usually we write polynomial functions with the leading term first. You don't have to, but hence the name leading term. Okay, so we almost always write the power function of highest degree first, and we call it the leading term. Okay, so transformations of power functions. A power function of the form f of x equals k times x to the n can be reflected around the x-axis if the leading coefficient is negative. This would change the end behavior of the power function as follows. So if we have an even power function, that's this left-hand column. If we have an odd power function, it's the right-hand column. And then if k is positive, that's the first row. For negative k, that's the second row in this table. Okay, so there's 4 possibilities because there's 2 possibilities for the power. It could be even or odd, and then the coefficient. It can't be 0, else it wouldn't be the leading term. So we just consider the cases where the coefficient k is either positive or negative. And so that leads us to these 4 possibilities where we have an even power function with a positive constant. The behavior of the function will be, sometimes we call this up, up. Okay. The full description is right down here, kind of describing the behavior algebraically. And so these little arrows you see in this thing I've circled are just read as goes to. So for example, we might read this as x goes to negative infinity, f of x goes to infinity. And as x goes to did I say negative infinity for the first one? I meant to. And as x goes to infinity, f of x goes to infinity. Okay. Whereas, notice for the odd power case but positive coefficient, we have as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x goes to positive infinity. And so on and so forth. Okay. So these 4 cases will be very helpful to us when graphing power functions and polynomial functions. So let's describe the long-run behavior and the degree of each power function. So this is degree 6, which is even. And so this is going to have this up, up behavior. I can do a little better than that, maybe. There we go. Okay, part B. This is degree 9, which is an odd degree. And so here we're going to get opposite behavior. And since the leading coefficient, it's really just a power function, but it's also a polynomial. And the leading coefficient is positive 1. So here, as x, I really probably should put some axes here. As x goes to positive infinity, this is my x-axis, the y values will go up to positive infinity. And as x goes to negative infinity, the y values will head off to negative infinity in this case. Part C, this is a degree 5 polynomial or power function, and it has a negative coefficient. So this is just going to be the reflection of the previous one, essentially. Not as steep, though, because it's not as high of a power, but its end behavior will be something like this. As x goes to positive infinity, as we take larger numbers and raise them to the 5th power, they're going to get very large, but we're multiplying all that by -3, so they'll get very large, but in the negative direction. And then vice versa, as we take negative numbers and raise them to the 5th power, very large in magnitude negative numbers, raise them to the 5th power, they become very large negative numbers. We multiply that by -3, and we get a positive result. And so the function will do something like this. Okay. Next exercise. Describe the long-run behavior of f of t. Okay, here we have a polynomial function in the variable t given to us in factored form. So what we need to the key is that in understanding how to determine the long-run behavior of a polynomial function is simply the knowledge that in the long run, as x gets very, very large in magnitude, either positive or negative, the leading term of the polynomial function will dictate the behavior. Why is this? It's simply because the highest degree term is going to grow much faster than all of the smaller degree, all of the smaller power terms in the polynomial. So how do we get from a factored polynomial into a polynomial in general or standard form? Well, we could multiply this all out, but notice this is there's squaring and cubing going on, and it would be a bit of work to multiply this all out. But there's a shortcut for getting the leading term of the polynomial, and that is just to take the leading terms in each of these factors and do the operation to it. So here we're squaring, so we have a factor of 3 out front. Here we're going to get, from this factor of the polynomial, we're going to get a t squared. And then from this factor, we're going to get a t cubed. And then from this factor, we're going to get a t cubed. And so if I were to simplify this out, I can combine all these powers of t, since they're the same base t. I just add the exponents, and I get 3t to the, let's see, that would be 8th power. Okay. So this is the leading coefficient of this polynomial. And this is all I need in order to determine the long-run behavior of the polynomial function. Okay, so it is even degree, and so the long-term behavior will be up. And because the coefficient is positive, it's even degree and positive, so the long-term behavior will be. And here's the thing, I'm gonna write a little cloud, because this polynomial can do all sorts of funky things near the origin in the short run, right? In the short run, for small values of t, this function could do lots of gyrations, so to speak, or changes in direction and such. But in the long run, for very large in magnitude values of t, the function will look like this, approximately. Okay, it'll go off to positive infinity as t gets very large in the positive direction, and it will also go off to positive infinity as t gets very large, but in the negative direction, large in magnitude. Okay, I just want to show a quick thing with the calculator to kind of to persuade you that the leading term of a polynomial is what really dictates the long-run behavior of a function. And so over here I've put in the functions. Y sub 1 is just the polynomial x, or the power function x. Y sub 2 is x squared. Y sub 3 is x cubed. Y sub 4 is x to the 4th. And I've graphed these power functions. The blue line, which looks flat. It's not flat, but it was the function x. Let me give you the scale for this, and let me make this a little bigger. Okay, so the blue line is just y of x equals x, and the scale on this graph, x goes from negative 100 to positive 100, and the y window, the y values go from negative, I think it was 10,000 to positive 10,000. Let me check the window. Yeah, y min is negative 10,000, y max is positive 10,000. Okay, so the blue line is y equals x. The red one is y equals x squared. Okay, the black is y equals x cubed, and then what is that, magenta or violet line is y equals x to the fourth. So notice the x to the fourth, it grows faster than all of the functions. X cubed grows faster than x squared, and x squared grows faster than x. Okay, so no matter, I also have a table in here. Let me see if I can get that. A table of values. So in this table, the x column, think of these are inputs to our power functions. And then in the subsequent columns, you see the output from each function, where the y sub 1 is just y sub 1 equals x, y sub 2 equals x squared, y sub 3 is x cubed, y sub 4 is x to the fourth. And compare, for example, the last row. So when I plug in 100,000 in for x, I just get 100,000 out from the first function, but I get 1 times 10 to this e notation is scientific notation. It means 1, so 1e10 means 1 times 10 to the 10th power, which is a 1 followed by 10 zeros. Notice the next one, though, you tack on 5 more zeros, or you multiply by 100,000. It's 100,000 times bigger in value. And if you go up to x to the fourth power, it goes from 100,000 times bigger than the quadratic to 100,000 times bigger than that. Okay, so the point is that the leading term of a polynomial function will completely dominate all of the other terms for large enough values of your independent variable, x or t or whatever you're using. Okay. Okay, so for polynomials, just like power functions, to determine the long-run behavior, all we need is the leading term. Okay, let's talk about short-run behavior of polynomials. So the short-run behavior of a polynomial describes the y and x intercepts. Or rather, I would say the x and y intercepts kind of dictate the short-run behavior of a polynomial, perhaps is another way to say it. And also the number of turning points of the graph of the polynomial. Okay? Since a polynomial is a function, it can only have one y-intercept. That is true of all polynomials. However, it can have several x-intercepts, also known as zeros or roots. These are found when setting the polynomial equal to 0. So basically, to determine the short-run behavior or the behavior of the graph of a polynomial for points near the origin, we need to find all of its x-intercepts and its y-intercept. You find the y-intercept by evaluating the polynomial at x equals 0, and you find the x-intercepts by solving the equation you get by setting the body of the polynomial equal to 0 and then solving for x. So, and then another important fact here is this. A polynomial of degree n will have at most n x-intercepts. Now, it could have fewer. So like a degree 3 polynomial may have 3 points where it touches or crosses the x-axis. It may just have 2, may just have 1, but it will always have at most equal to the degree x-intercepts. Okay, and a polynomial of degree n will have at most n minus 1 turning points. So a 5th degree polynomial could have up to 4 turning points, but it doesn't have to have 4 turning points. it really depends on the number of unique zeros of the polynomial. So we can have what we call a repeated zero or repeated root of the polynomial, and that changes how many times you'll have a term, or it can change that. We'll see examples of this. So here we go. The first polynomial graphed below is f of x equals x cubed minus x. This is a degree 3 polynomial, so it can have at most 3 x-intercepts, and indeed it does have 3 x-intercepts. One right here, one here, and one here. And notice the x-intercept is also the y. It goes through, the graph goes through the origin, so our y-intercept is also coincides with an x-intercept. That can happen. Next, we have a polynomial of degree 4. So this could have up to 4 intercepts. But there's something special about this middle intercept. Okay? Notice that the graph of the function just touches the x-axis at that intercept. If I were to factor this function, I would get x squared times x squared minus 1. Okay? And if I factor x squared minus 1, it's a difference of squares. I'd get x plus 1 times x minus 1. That gives me these two roots or zeros on the outside. But notice this x squared factor at the beginning there. I could rewrite that x squared as x minus 0 quantity squared. Okay, so it's a little more clear that the zero, the value of x that makes that 0 is 0. Okay, but the point is, though, is that the degree of this factor is its degree 2, or it's an even degree. Whenever you have an even degree, the graph of the function will just touch the x-axis at that 0 instead of crossing. However, whenever you have an odd degree factor, then that factor will cross the x-axis at that 0. Okay, we'll see more examples of this coming up. Notice in the first case, I could have rewritten this as what? As x times x squared minus 1. And then the x squared minus 1 is a difference of squares, so it would factor and become x plus 1 times x minus 1. But it would give us 3 distinct zeros, each with a power of 1 on them. We also call that power of the factor the multiplicity of the 0, how many times that 0 gets repeated as a factor in the factorization of the polynomial. And since each 0 here just occurs once in the factorization, notice that the graph goes through every single 0 here. It doesn't just touch the x-axis, it crosses the x-axis at every single 0. Let's look at this third example graph here. We have x to the 6th minus 3x to the 4th plus 2x squared. Okay. Well, clearly I could factor x squared out. Yeah, I didn't think about how to factor this one. We'll just move on this one. That doesn't seem right to me. Yeah, I think we'll move on this one. Okay. Exercise. Find the degree, leading coefficient, and the maximum number of zeros of the polynomial f of x equals -4 minus 6x to the 7th plus x to the 8th plus 3x to the 5th. Okay, well, this polynomial is not written in your standard format. We can fix that, though, because the leading term should be the term with the highest power, in this case, which is 8. So the leading term should be x to the 8th, followed by minus 6x to the 7th, followed by this positive 3x to the fifth, followed by the constant term minus 4. Okay, so here is my leading term of my polynomial. The power is 8, so the degree of the polynomial is 8. And the leading coefficient, there's an implied positive 1 there. So this could have, at most, 8 real zeros. It doesn't have to have 8 real zeros, but in fact, it could have 0 real zeros. Even polynomials don't have to have any real zeros. Odd polynomials, though, always have to have at least 1 because they have that opposite long-run behavior. So the graph, since it's a continuous function, the graph must cross the x-axis at least once. So every single odd degree polynomial has at least 1 real zero, but not so of an even degree polynomial. Think of x squared. You could have a parabola that's vertex is above the x-axis and it opens up. Okay, so even degree polynomials do not have to have any zeros. All right, moving along. Okay, we'll just ignore, I did a little work previously. Let's just ignore what's in the box for right now, and we'll answer the question. So what is the least possible degree of the polynomial? Okay, so we have the graph of a polynomial, and we want to determine, well, what is the smallest possible degree this polynomial could have? I notice that there is, let's see, 1, 2, 3, 4 zeros, and the thing about these zeros is that the graph crosses at each one of them. So that means the multiplicity of each zero is odd, and the smallest odd number is 1. So so there's 4 zeros, the smallest, and how many turns do we have in this polynomial? Well, we turn, I'll put a little x at the places where it turns. We have a turn where the function goes from increasing to decreasing at that x, similarly right here, and then similarly right here. So we have 3 turns, which is 1 less than, remember, the highest number of turns that a polynomial function can have is n minus 1, where the degree is n. So we have 4 zeros and 3 turns. This could be the smallest degree that this polynomial could be would be 4. Okay. If we wanted to figure out the actual polynomial, what we could also use, that doesn't ask us to do this, but this is a favorite idea used on exams, right, is can you figure out what polynomial this is? What is the actual function? Well, and that's what I've done here in this box. I know I have a 0 at x equals -3, so I get this factor of x minus -3, which is, of course, the same as, we don't usually write it that way, we just write it as x plus 3, which gives me this first factor here. And then the 0 of 1 gives me this factor, x minus 1. The 0 at 3 gives me this factor, x minus 3. The 0 at 4 gives me this factor at x minus 4. Now, I could scale the polynomial, stretch it in the vertical direction, or compress it in the vertical direction, or also flip it. And so I put a factor of k out front. Okay, that's just, k is just representing an unknown number. Okay, it doesn't increase the number of zeros of the polynomial. What it's going to do is allow us to figure out, to get it so that the polynomial has a y-intercept of 1. Okay, so I've expanded this out here, and you can follow along if you want. And you see that I get this k times x to the 4th minus 5x cubed minus 5x squared plus 45x minus 36. Okay. Oh, I actually have small mistake here. My k should be negative 1 over 36, shouldn't it? In order to get a y-intercept of 1, notice that the y-intercept of a polynomial always corresponds with the constant term at the end. Okay, because if you plug in 0, the way you get your y-intercept is you evaluate the polynomial function at x equals 0, and all of the terms before the constant term will evaluate to 0, so I'm just going to get the constant term when I evaluate at 0. But in order to get it to be 1, I have to have this factor of negative 1 over 36 sitting out front, right? And then because when I distribute that factor to all the terms in parentheses, I'm going to get a plus 1 at the end. Okay. So we can go forwards and backwards. Given a polynomial, we can graph it, or given the graph of a polynomial, we can determine what the original polynomial was. Okay, and one of the key ideas is that one last thing I want to point out is that to get if we have a polynomial in factored form, to figure out the y-intercept, all you have to do is multiply together all of the constant terms in all of the factors, taking into account any powers, like if a factor is squared or cubed, you have to take that into account as well. But okay. How about this? What is the c-intercept and the n-intercepts of the function c of n equals n minus 7 times n plus 6 times n minus 4? So this polynomial is presented to us in factored form. And again, what I've done is I've rewritten this. I've expanded this polynomial out from factored form to standard form. And notice what happens is the c-intercept here is the c is the independent variable, n is the dependent variable. So c is like, the c-intercept is the same as like the y-intercept. It's the vertical axis, right? And to get that, the thing I want to point out is that, in other words, to evaluate this function when it's in factored form, to evaluate it at 0, that is, all I have to do is put in 0 for n, and what am I going to get? I'm going to get negative 7 times positive 6 times negative 4, which is going to be 42 times 4, which is 168. Okay, so notice that this 168 agrees with what we would get from expanding the polynomial out from factored form to general form. What about the n-intercepts? Well, the beauty of having the polynomial in factored form is that the n-intercept, so this is the c-intercept, and the n-intercepts, these are going to be at n equals 7. These are just the values that make those factors 0, the values for n. Negative 6 and positive 4. Okay? So we kind of like having our polynomials in factored form because it makes getting the n-intercepts very easy, or x-intercepts, the independent variable intercepts. Next exercise. What is the g-intercept and the r-intercepts of the function g of r equals 3r to the 4th plus 33r cubed plus 90r squared? Now this function is not given to us in factored form, and to find the r-intercepts here, r is the independent variable, what we're going to have to do is we're going to have to factor the polynomial. So g of r, let's see, I can factor, every single term has a factor of 3 in it, and at least r squared. So I can factor 3r squared out of all terms. And then I'm going to have r squared plus 11r plus 30 plus 30. Yeah, there we go. Okay, does that trinomial, that quadratic trinomial, factor further? I think it does. It factors to r, let's see, plus 5 times r plus 6. Okay. So then, notice the g-intercept, same as idea as the y-intercept. Just evaluate the function at r equals 0. When I plug in r equals 0 into this function, of course, I get 0 out. I'll write it as a coordinate pair, so it'll be, whoops, it'll be 0, 0. What about the r-intercepts? I'll write these as pairs as well. Well, we have, so r equals 0, or -5, or -6. So the pairs, the points on the graph will be, so here the y values will all be 0. So we'll get 0, 0, and -5, 0, and -6, 0. Those are our intercepts. Okay, continuing on. Sketch the graph of the function f of x equals x times quantity x plus 3 squared. Okay. Two things we need to determine: long-run behavior and short-run behavior. That x plus 3 factor squared, that's going to give me a quadratic, or degree 2, and then I multiply that by x, I'm going to get a degree 3 polynomial. And if I multiply all my leading terms together, I'm going to get x squared times x. I'm just going to get x cubed. So my leading term would be 1x cubed. So this is an odd degree polynomial. And so my long-term behavior will be, I could have some weird behavior going on here near the origin, but away from the origin, it'll be like this. So that's my long-run behavior. Now, what about my short-run behavior, my intercepts? Well, what is my y-intercept? I just evaluate the polynomial at x equals 0. At x equals 0, I get 0 out. I'm just going to write this as a number, not as a pair. What about x-intercepts? It's already in factored form, so the x-intercepts, we can just read those right off. We have 0 and -3. I also like to write down the multiplicities. So notice that the that -3 is a repeated 0 of this polynomial, isn't it? Or we say it has multiplicity 2. So the first 0 at x equals 0 has multiplicity 1. But the second 0 has a multiplicity of 2. And the multiplicity is important because it tells us whether or not the graph will just touch the x-axis at that 0 or cross the x-axis at that 0. Okay, so now how do we graph this? What we're going to do is just graph all of the intercepts, and then we'll sketch in the long-run behavior, and then we'll connect everything up with a smooth line. Okay, so our y-intercept is here at the origin. We have an x-intercept at 0 and at -3. Okay. Now don't need the multiplicity yet. What I'm going to do next is take into account this long-run behavior. So what I'm going to do is just a little to the right of the rightmost 0, I'm going to put an up arrow. And then a little bit below and to the left of the leftmost 0, I'm going to put a down arrow. Okay? Now the idea is I need to connect these arrows with a smooth curve that goes through or touches those zeros as dictated by the multiplicity. So the multiplicity of the 0 at x equals 0 is 1. So here we need to go through the x-axis there. So I'm going to do a little line. Obviously, I have to connect up with what's above. Okay? But the multiplicity of this other 0, it's 2. It's even. So the graph will just touch the x-axis at that 0. And so I'm going to get behavior kind of like this. Okay. Okay, so I just put these little crib notes on each of my zeros. I put a little line either going one way or the other, and then I put a little like parabolic shape either below or above, and I'm using my hints from my long run behavior to determine which way to draw those little crib notes on my zeros. And now I connect everything up with a smooth line. I want to connect this up, I want to connect this up, and then I want to connect that. Okay, now not a great nice smooth graph, but qualitatively it's correct. It gives us the rough behavior, the qualitative behavior of the function. Okay, you know, how far does this come down? It could come down a great deal. We don't know. And we need calculus really to kind of figure that out easily. I mean, you could always just plot some points, you know. It doesn't hurt to plot a couple extra points using the function, but not necessary here. We're really just interested in the qualitative behavior. Okay, let's try the next one here. Ah, good. Our function is already factored for us. First, though, let's determine the long run behavior. Let's see. We have three binomials all multiplied together. So each one has x to the first power. When we multiply this out, our leading term will just be x cubed. So this again will be we'll have some behavior in the middle here, but the long-term behavior will be this kind of behavior. Okay, what about short-run behavior? What about the y-intercept? To get this, I just evaluate the function at x equals 0. And when I do that, I'm going to get, let's see, -2 times -4 times -3. It's going to be negative. And it's 2 times 4, which is 8, times 3, it's 24. So -24. Okay, I can't even get that on the graph. What about the x-intercepts? Well, we have one at x equals 2, 4, and 3. I'll do them in ascending order, 2, 3, and 4. And they're all multiplicity 1. Okay, so the graph will cross the x-axis at each one of these zeros. So let's see. So now that I've gathered all this information to graph the polynomial, I'm going to start by plotting the intercepts, and then I'll put in the arrows for the long run behavior, and then I have to use the multiplicities to write in my crib notes on my zeros, and then finally connect everything with a smooth line. So let's see, I can't plot my y-intercept on this set of axes because they don't go down far enough, but I'll just kind of remember there's a point way down here that it's got to go through, and we're going to go through the points 2, 3, and 4. Okay. Okay, so now I've plotted all of my intercepts that I could. Now I plot the long run behavior, this guy. So just to the right of my rightmost 0, I'm going to put an arrow pointing upwards. And to the left of my leftmost 0, I'm going to put an arrow pointing downwards. And now I need to use the multiplicities of my 0. They're all odd, so that means the graph will cross at each one of these zeros. So just put some crib notes on here. It's got to cross like this, and then that. Okay, and now I'm just going to try and connect these lines up. Whoops. As good as I can here. And there we go. Whoops. Okay. Good enough. That's the basic qualitative behavior of the graph. And yeah, notice my graph's going to come down and hit somewhere very negative on the y-axis. Okay. Next, we don't have an equation, we have an inequality. Okay, so solving an inequality can be done two different ways. I think the simplest way is to just graph the polynomial. Okay. So let's see here. What is the end behavior of this polynomial? Well, I have -4 times that -5 gets squared. So I get positive 25. So I have -4 times positive 25. That's going to be -100. Okay, so I went from trying to determine the long run behavior to getting the y-intercept. Sorry, brain fart. But y-intercept is at -100. The long run behavior, sorry, will give me, I'll have an x times an x squared. That'll be x cubed. So I'll have same as before. As the last two. I'll have this kind of behavior. Okay, what about x-intercepts and their multiplicities? I have an x-intercept at 4 and one at 5. And the multiplicities are 1, or odd, and 2, or even. Okay. I can't plot that y-intercept, but I can plot the x-intercepts here at 4 and 5. Okay. Now that I've plotted my intercepts, I'm going to plot the long run behavior. So I have this kind of behavior. Something like that. And let's see here. The multiplicity at 4 is 1. It's odd, so the graph will cross here. The other one is even, so the graph will just touch. So here I've got to come from above and come back down and just touch. So I'm going to have this kind of behavior at that 0. It's going to touch from above. Okay, so I've got my crib notes from using my multiplicities, and now I'm going to connect up the lines. So that, there, and there we go. Something like that. Now, are we done here? No, we're not done. We need to answer solve the inequality. So where is this function strictly less than 0? Well, it appears to me that it's greater than or equal to 0 at 4 and above. So really, it's all the x values from here over. that satisfy the inequality. The x values to the right of that line do not satisfy the inequality. So our solution set would be the number line from, or the subset of the real line from negative infinity to 4, but we don't want to include 4 because we have strict inequality. So there we go. That's the solution set. So we get a whole infinite range of numbers that satisfy that inequality. Okay, last exercise in this section. Find the domain of the function f of x is equal to the square root of 24 minus 14x minus 3x squared. So this is not a polynomial function, but the argument to the square root function is a polynomial function. And recall that the domain of the square of any even root function, this is a square root and hence an even root, the domain of any even root function is all numbers greater than or equal to 0. So to get the domain of the composite function, what we need to do is set 24 minus 14x minus 3x squared. This has to be greater than or equal to 0. The square root of 0 is just 0. That's perfectly fine. So this is the inequality we wish to solve. It doesn't look like we have a factor of 3 in all the terms. 14 is not divisible by 3, so I can't factor that out. Bummer. And I usually like to rewrite it in the standard form, 3x squared minus, negative 3x squared minus 14x plus 24 is greater than or equal to 0. And, well, I really don't like having that lead coefficient be negative. So I'm going to multiply both sides of this inequality by -1, remembering that I need to flip the direction of the inequality symbol. So I'm going to have 3x squared plus 14x minus 24 is less than or equal to 0. Okay. I think I can factor this now. I think this will be 3x and x. Okay. And I need two numbers which multiply to 24. But then, let's see. 4 and 6. Let's see. Yeah. If I do a 4 here, 6 here. Yeah. Okay, let's just double check that. When I multiply the lasts, I get -24. When I do the firsts, I get 18, positive 18x. When I do the inners, I get -4x. Positive 18x minus 4x is positive 14x. And I do get positive 3x squared. Okay, so that checks out. That is a correct factorization. So let's see now. This is a polynomial which opens upward. And I want to know where is this polynomial less than or equal to 0. It has zeros at, let's see, x equals 4/3 and -6. Okay, I'm just going to do a quick little graph here. We'll say -6 is here. 0 might be around here. And then 4/3 might be right around here. There we go. Now, do we want to include the zeros in our solution set? Yeah, because this is non-strict inequality, so I'm going to put some closed circles there. And of course, since this is a parabola which opens upward, I'm just going to put something in like this, and then I can do a little better than that, perhaps. There we go. So let's see. The inequality is satisfied by all the points, all the x points in between the two zeros and including the endpoints. So my solution set would be from -6, including that point, to 4/3, including that point. And there we go. And this concludes section 4.2 on polynomial functions.